Hi, it's Mrs. Moret with help on today's assignment, the Lesson 5 practice problems. So the big idea for today was for you to understand that in an exponential function, the factor, either growth factor or decay factor, will remain the same over intervals that are equal. So like from 0 to 1, the growth factor will be the same as from 1 to 2 and 3 to 4, but also the same as like from 0.5 to 1.5, because that's also an increase of 1. So we're going to apply that understanding with these practice problems. So first, the table shows the monthly revenue of a business rising exponentially since it opened an online store. I noticed in this table that the values given are for 0, 3, and 6 months. So it looks like then it's counting like it's raising by so much every 3 months. So describe how the monthly revenue is growing. So it's growing by, I need to figure out the percent. And so to figure out the percent, grab my calculator, I have to figure out what's 90,000 divided by 72,000. 1.25. So if it's growing by 1.25, that's going to be the growth factor, but it's every 3 months. So I could say it's growing by 1.25 every 3 months. But then what does that mean monthly? So if I just wanted to know what's it going to grow by each month, and my current data is for every 3 months, so I'm just going to use a fraction exponent. 1.25 to the 1/3 every month. Okay, so since the information that we have is the factor for every 3 months, in just 1 month, it would be 1.25 to the 1/3. Okay, and that will help us with part B to write an equation that represents the revenue as a function of months, so single months since the store opened. And so this is just for 1 month, but I can replace that 1 with a variable and have it be for any number of months. Just have to divide by 3, since what we're given so far is information every 3 months. And so I'll say R of M using function notation. The initial amount, 72,000. The factor, 1.25. And then I'll say M divided by 3 for the exponent. Okay, find the monthly revenue 1 month after the online store opened and record the value in the table. So I'm just going to use this information that we came up with up here. So I'm going to take the starting amount and then multiply it by 1.25 to the 1/3, since this is what it would be growing by each month. So 72,000 times 1.25 to the 1/3. If you have an older calculator, you actually have to put the exponent in parentheses in order for it to calculate correctly when your exponent is going to be a fraction. All right, so it looks like approximately, I'm going to say 77,560, just to round it. Okay. And then how can we use the value of R1? So this is D here. How can we use the value of R1 to find R4? Well, this is a jump of 3 months. And we know that in this function that the factor it grows by is 1.25 every 3 months. So we can just take our value for R of 1 and multiply it by 1.25, since that represents what happens in 3 months. And that should give us the value for R of 4. Okay, so I'm just going to keep my answer as is in the calculator. I still have the R1 value in there, and I'm going to multiply it by 1.25. And so it looks like R4, or the 4th month, is 96,949 and some change, so I'm going to round it up, 96,950. And just as a side note for you, I wanted to show you that we would get the same answer if we started with R3 and use that exponent of 1/3, since this is just 1 month later. So I'll just show you. 90,000 times 1.25 to the 1/3. So we should get the same 96,949. And look at that. It's exactly the same. Okay, on number 2, I always think these bacteria problems are so gross, but very realistic. So it says at 7 a.m., a colony of 100 bacteria is placed on a petri dish where the population will triple every 6 hours. So triple, that's multiplied by 3 every 6 hours. Select all statements that are true about the bacteria population. So I'm just going to check to see if these are true. When the bacteria population reaches 12 hours, when the population reaches 900, 12 hours have passed since the colony was placed on the petri dish. So this 12 hours means it would have tripled 2 times, since it triples every 6 hours. So this would triple 2 times. Okay, so what I'm going to do then is check. 100 times 3, so it's tripling, and that's going to happen 2 times, 3 to the second. And look at that, it equals 900. So A is a true statement. Okay, for the next one, 3 hours after the colony is placed on the petri dish, there are 200 bacteria. So 3 hours out of the 6. So I'm going to say, okay, well, 100 times 3, but now it's just for 3 out of the 6 hours. And so I could use a 1/2, I could use a 3/6. They, equal the same thing. And it looks like that is 173 and such, so not 200, so B is not true. C, 3 hours after the colony is placed on the petri dish, there are about 173 bacteria. Yes, I just did that for 3 hours, so C is a true statement. D, in the first hour the colony is placed on the petri dish, the population grows by a factor of 3 to the 1/6. So it says in the first hour, where it triples every 6 hours. So it's tripling, and then it's 1 out of 6 hours, so that is a true statement. And then finally, between 8 a.m. and 9 a.m., the population grows by a factor of 3 to the 2/3. That's not a true statement. This is a change of only 1 hour. And if it triples every 3 hours, if it triples every 6 hours, as stated in the problem, then it would be 3 to the 1/6. Okay, because That's only 1 hour, and it takes 6 hours to triple. So 3 to the 1/6. All right, number 3. So the graph represents the cost of a medical treatment in dollars as a function of time D in decades since 1978. Find the cost of the treatment in dollars when D equals 1 and show your reasoning. So what I notice here is that I have information for when D is 0 and when D is 0.5. So I have that first interval from 0 to 0.5, and that's an equal interval of time from 0.5 to 1. So if I can figure out what the factor is between 150 and 202.5, I can then use that to figure out when D is equal to 1. Okay, so I'm going to make a little table just to kind of explain that a little bit more. So I have D for decades, and I'm just going to say C for cost. Okay, so according to the graph, in decade 0, which is 1978, cost is 150. And then 0.5, which would be half a decade later, the cost is 202.50. Okay, so I can use that to figure out the cost one decade later, or in, what is that, 1988. All right, so I'm going to calculate the factor between 0 and 0.5. So 202.50 comes first, and then divide by the number before it, 150. So from here to here, we multiply by 1.35. So if I multiply that answer by 1.35, then I get, oops, I multiplied the wrong thing, sorry. If I multiply this amount, 202.50, by 1.35, that's what I meant to say. Then I get the amount, half of a decade later in decade number 1. Okay, so 273, I'd say 38, round that up. And that's what it's asking for. Okay, number 4. The exponential function f is given by f of x equals 3 to the x. By what factor does f increase when the exponent x increases by 1? Explain how you know. So I would say, okay, so we have, when we plug in this value for x, for the exponent, if it increases by 1, then we're just going to be increasing by, the factor is going to increase by a factor of 3. And how do I know that? How do I know that? So I can just kind of show an example. So I have 3 to the first. And if I just increase this by 1, 3 to the second, 3 to the third, 3 to the fourth, and so on. So each time, this is increasing by a factor of 3, right? There's one more 3 being multiplied on there. But then if we increase by the x values by 2, and let's say we go ahead and still just start with 3 to the first, the next one is 3 to the third, and then 3 to the fifth, and then 3 to the seventh. Okay, so each time in the first set for A, so each time here, I'm multiplying by one more 3, right? 3 to the second, 3 to the third, that's multiplied by 1, 3. 3 to the third, 3 to the fourth, that's times 3 again. But here, in between these, 3 to the first to 3 to the third, that's a difference of 3 to the second. Now I'm multiplying by 3 to the second. So my factor is increasing each time by 3 to the second. Okay? So then on part C, what factor does f increase by when the x increases by 1/2? Well, the same thing's going to happen kind of following the trend. It's going to be increasing by, this was 3, this was 3 to the second, and this should be 3 to the 1/2. Now, I'm going to actually represent this with the decimals, 0.5. But if I go, okay, my first term is 3 to the first again, then I'm going to increase the exponent by 1/2. So that would be 3 to the 1.5. And then another half would be 3 to the second. And another half would be 3 to the 2.5. Okay? So again, if we look at how are these changing, this is by 3 to the 0.5. This is by 1.5 up to 2, 3 to the 0.5. Okay, which is the same thing as 3 to the 1/2. So as we increase our input value for the exponent, whatever we increase that by, the factor increases by that power. So we increase the exponent by 1/2, which means the factor is increasing by 3 to the 1/2. We increase the exponent by 2, so the factor is increasing by 3 to the second, and then increasing the exponent just by 1, the factor is simply increasing then by 3 to the first. Okay, number 5. A piece of paper has an area of 93.5 square inches. How many times does it need to be folded in half before the area is less than 1 square inch? Explain how you know. So if I'm going to take this and every time I fold it, the area is going to be half of what it was before. Sorry, I was trying to find that spot in the prompt. The area is going to be half of what it was before. So 93.5 times half, or 0.5, to the x, right? And I want to know, when's it going to be less than 1 square inch? Well, later in this unit, you're going to learn how to actually solve this to get an exact answer. But right now, we're just going to kind of do a little guess and check. And the most efficient way to do a guess and check is going to be to make a little table in my calculator. Okay, so 93.5 times 0.5 to the x. Okay, so I'm going to program that in there. And then I'm going to look at the table. Second graph is how I get to the table. And I'm looking for, oh goodness, I have this set at a really large number. So I'm going to just second window and have my table start counting at 0. And then go back to the table. Okay. So I can see it actually happens pretty quickly. After 6 folds, it's 1.4, and after 7 folds, you can see it's now less than 1. So I'm going to say after 7 folds. Okay, and then finally for number 6, the area covered by an invasive tropical plant triples every year. Triples every year. By what factor does the area covered by the plant increase every month? Well, since there are 12 months in a year, Okay, since there are 12 months in a year, each month it's going to be 1/12 of the year. So tripling means to multiply by 3, but if it's every month, it's going to be the number of months divided by 12 because there are 12 months in a year. So after 1 month, it would be 1/12. After 2 months, it would be 2/12, and so on until you get to a full year. Then that would just be 3 to the 12/12, 3 to the first, just tripling. All right, that is the end of your assignment. I hope you found the video helpful.